Okay, so let us now start this. So this is one of the very important theorems, that continuity implies integrability. So if I want to summarize this, I would say that if you give me a function which belongs to the continuous functions on this interval, then it is granted that this is also Riemann integrable. So this is the summary of that theory. So we'll go to a sketch of the proof. I want you to understand this a little bit deeper. So I want to use some theorems from the previous lessons and one theorem which is the Riemann integrability criteria. If I want to prove that my function is Riemann integrable, I would say that let epsilon greater than 0 be given. We prove that there exists a partition of P a partition of A and B, sorry. There exists a partition of A and B such that a U, F, and P minus L, F, and P is less than epsilon. So remember, someone has given me an epsilon. My duty is to find a partition so that this works. Okay? But the assumption that I have in my hand is that I know my function is continuous on the closed interval from A to B. Okay. So what we do here is a little bit, so you need to remember some theorems. So F is continuous. Yes. And then you know that A and B is compact. So what can I conclude from here? Do you remember Max-Min theorem? Not Max-Min theorem. We had a theorem that if F is continuous on a compact set, it is also uniformly continuous there. So F is continuous, but this one is compact. A function which is continuous on a compact set is also uniformly continuous on that set. That was one of the main theorems we had before. So F is uniformly continuous on A and B. So what does it mean? It means for every epsilon, I can find the delta so that if the difference between 2 points is less than that delta, the distance between the corresponding F values is less than any positive epsilon. But I want to write the epsilon in a little bit a strange way, and you will see why it works at the end, okay? But you need to understand what I am writing here is true. It is not a lie, okay? So this means that according to this epsilon, I can grant the existence of a delta such that for all x and y in the interval from A to B, if the distance between x and y is less than delta, then the absolute value of the difference between the m values is less than any positive number. I want to construct a new positive number based on the epsilon that you gave me. You might say, why? You have to be patient and see this works. And no one actually came up with this in the beginning. They did some scratch work and they realized what they have to choose here. The choice is a little bit strange. Yes? But I want you to understand everything that I have written here is completely correct. Yes? F is continuous, this is compact. If a function is continuous on a compact set, F is uniformly continuous. So this means for any epsilon, including this positive value epsilon. This is also a positive value, yes? B minus A is positive. epsilon divided by that's a positive number. So you can grant the existence of a delta that this implication works for every choice of x and y in your set. That's the meaning of uniform continuity. Do you remember that? Okay, so why this is important? Okay, so now what we do like this. I am looking, we prove that there exists a P. Now I make a claim and we prove our claim. So, claim is that if P, if norm of my partition is less than this delta, okay, so let me write it like that. If that happens, this delta is the delta I get it from this factory, yes? You give me an epsilon. According to what I told you here, I give that epsilon to this factory. This factory will give me a delta. And I put this delta, and I want to use delta to prove that the existence of such a partition. I am claiming that if the norm of my partition means the longest length is less than this delta produced by this, then I am achieving this goal. Yes? So I want you to understand the logic. I gave you an epsilon. I am waiting for you to give me a partition so that this works. You take that epsilon, construct a new epsilon out of my epsilon in this way, and feed it to this factory, uniform continuity factory. This factory gives you a delta with that property. And now we claim that this delta that you got here is the one that will help you to find your P. How? You just need to find the norm. You just need to adjust the norm of your partition less than this delta. It will grant you this. But now I have to prove this. So how can I prove this? I start calculating this for you. But the calculation of this one is very simple. So I would say sigma mk minus mk delta xk. K goes from 1 to n. Okay? I hope that this calculation, I'm just subtracting the LUN. Okay, so now look. This one, mk, because my function is now continuous on a closed interval, it will also attain its maximum and its minimum, which was Max-Min theorem. Yes, what does it mean? This is the maximum. There is no difference between supremum and maximum because my function is continuous. So if I ask you what is mk, you will tell me there exists a p sub k in the kth interval such that mk is equal to f of pk. Do you agree with this one? Because m is the maximum, and because my function is continuous on a closed interval, it attains its maximum. So it means that you can find a number within this interval whose value is exactly m sub k. And then, exactly like this, you can also grant the existence of a q sub k in the same interval, such that what happens, m little k is f of x, f of this one. So that's very simple. This is maximum, this is minimum, but my maximum and minimum are attained. So it means that maximum is f of a particular number, is a specific number here, and m sub k is the value of f at some point here. So if you put everything back there, so what happens, I put them here. So this becomes equal to sigma, k goes from 1 to n, f of p sub k minus f of q sub k, and then delta xk. I know that I have to put a pair of brackets here, but if I put absolute value, do you complain? So in principle, I know that I have to put a pair of brackets, but if I put absolute value, do you complain that they are not the same? No, because m sub k is maximum, little m sub k is minimum. So m sub k minus m sub k is positive. So it doesn't matter if I put absolute value or pair of brackets. Why did I put absolute value? Because I want to make it very similar to this one, okay? So now what I write, do you agree with this one or not? So I would write that one. This is less than or equal to sigma k goes from 1 to n. Instead of this one, I put epsilon over b minus a. Is that understandable? Why? Because it tells me that if the distance between my numbers x and y is less than delta, this is granted for that pair. Okay? So my question for you is that, is it guaranteed that the distance between p sub k and q sub k is less than delta? So let me ask this question. Because I am using this for p sub k and q sub k. So you need to tell me, is it true that this one is less than delta or not? Because if you agree that this is the case, then I can use this implication. This implication tells me that if the difference between my numbers is less than delta, the difference between the values of the functions at those points is less than epsilon over b minus a. So for the time being, do you agree with this one or not? Where is p sub k? P sub k is in the kth interval, which is part of the bigger interval. And q sub k is also there. Can you tell me why the difference between them is less than delta? Because I am assuming what? I am assuming that the norm of my partition is less than delta. So this means that the maximum length of subintervals is less than delta. So this means that the length of each one of these intervals is also less than delta. And these 2 points are chosen from this kth interval. So the distance between them cannot go beyond delta. Is that right? Okay, so this is for granted. Why? Because norm of p is less than delta. I can have this. And then, because this is true, this means f of pk and absolute value of f of pk minus f of qk is less than that number. But now this is a positive, this is a fixed number. I bring it out. And then I will have sigma k goes from 1 to n delta xk. But what is this number? Do you remember? I am adding the lengths of all subintervals. It becomes the total length, which is b minus a. And this b minus a cancels that b minus a. So then you get your epsilon that you wanted. So this justifies why we chose it here. You couldn't anticipate you have to choose it here. You need to continue up to here and then go back and fine tune your epsilon so that it gives you exactly the epsilon that you want. So that's it. Okay. Anyway, so this means that if a function is continuous, it is also integrable. And the notion of uniform continuity and compactness are the ones that are used in this theory. Okay, but then the question is that, is it the case that if we have this continuous function, it is automatically not continuous and not integrable? The answer is no. Okay, so this theorem tells me, so let me go to the next slide. Theorem 12.4 tells us that continuity is a sufficient condition for Riemann integrability. However, continuity is not a necessary condition. As we saw in the previous example, that is a little bit bad. In the notes, you'll really see an example, but here we didn't see an example. So if you go to the notes, there are examples that I have given you there, which are not continuous, but still the function is integrable. Okay, so remember, if the function is continuous, it is Riemann integrable. Or if you can say that if f is not Riemann integrable, then f is not continuous. This you know, this is true. This is also true. But if you just converse them, it is not true. There is no guarantee that if f is integrable, it is continuous. No, this is not the case. There are functions that are integrable, but they are not continuous. And I have given you some examples in the notes. Okay, so this is also, yeah, I have repeated it again with some other words. Okay, so let me read this. This is a good remark. So this theorem tells us that every continuous function on a closed interval is Riemann integrable. However, this theorem should not be misunderstood as saying that only continuous functions are Riemann integrable. The Riemann integral is more flexible than that. It can tolerate some discontinuities. The reason is that the Riemann integrability is not asking whether the function behaves perfectly at every single point. Instead, it asks whether we can make the gap as small as we want by choosing suitable partitions. Okay, so don't think that if the function is not continuous, then it is not Riemann integral. Okay, so this is one of the theorems that I will skip, but I want you to know it. I will not be able to prove it here. I have written the proof completely in the notes, and I recommend you to just choose one discontinuity. What is the content of the theorem? The theorem tells you that let f be a bounded real-valued function on the closed interval from a to b. Suppose that f is continuous on a and b, except possibly at finitely many points. Then f is Riemann integrable on a and b. So if I want to find the difference between these two theorems, the main theorem tells you that you have a function which is continuous everywhere on the interval. But this theorem tells you that no, the situation is not that serious. If you have some discontinuities, but the number of discontinuities is finite, you have 10 of them, 100 of them, 1,000 of them, still your function remains continuous. Integral. So be careful. The perfect scenario is that my function is continuous everywhere. It is Riemann integrable. But if I have a function, let us say this is A, this is B, and then I have a bunch of discontinuity points. For example, let us say that I have 3 discontinuity of the function. It still remains integrable. Okay? So as soon as I have only finitely many discontinuities, then the function remains still integrable. The proof is a little bit more technical, and we don't have that much time for it, but I want you to know the theorem itself. Okay, another theorem that is very simple to prove, I will prove it for you so that you can have some more practice, and that is monotonicity. So monotonicity means that either the function is increasing or decreasing. If the function is increasing or always decreasing, it is automatically integrable. Okay, so let us prove one of them here. So theorem 12.8. So let us say that f is increasing. One of the possibilities that for increasing. You can prove similarly for decreasing. So f is increasing on a and b. We want to prove that f belongs to a Riemann integrable function, the set of Riemann integrable functions. Okay, so if you want to do that, I will take the regular partition again. So let Pn x naught up to xn be the regular partition of A and B with a partition, because there are so we have to write this because there's only one. And let this be the regular partition of with n plus 1 nodes, yes? I want to calculate u of f of Pn minus L f of Pn. Okay? I want to use the Archimedes-Riemann integrability criterion. Yes. So this becomes exactly as before, the limit, the sigma of capital M sub k minus little m sub k delta xk, and then k goes from 1 to n. And now I know that my function is increasing. So if this is A, this is B, my function starts from here and it increases, for example, up to B, okay? So it increases. And let us concentrate here on the kth interval. Yes? Okay, can you help me to write something for Fk, Mk, capital Mk? This is my function, increasing function. Let me call it function F. So capital Mk, because the function is increasing, do you agree capital Mk is here? And little m sub k is the minimum or is the infimum is here. Okay? So if I want to continue, this becomes sigma. Instead of mk, I write the value of the function at xk. Yes? So it becomes f of xk minus little m of k means this height. This height is f of x sub k minus 1. Yes? K goes from 1 to n. And because I am working with regular partitions, the length of all of them are equal to b minus a over. But this one is a constant. I can pull it out. Sigma f of xk minus f of xk minus 1. K goes from 1 to n. But do you see what can I do with that sum? That sum is possible to calculate. It is a telescopic sum. Yes? So this becomes simply b minus a over n. And this becomes f of xn minus f of x naught. Because this is like a telescope. If you put 1, it becomes f of x1 minus f of x0. If you put 2, it becomes f of x2 minus f of x1. And if you continue, you see term by term they will cancel. One term from the first one is left, one term from the last one is left, which is this one. But if I ask you what is xn, xn is the last point, which is b, and x naught is the first point, which is a. So this is simply b minus a multiplied by f of b minus f of a, everything divided by n. Okay, so do you remember? I found a difference of upper sum and lower sums like this. Now I calculate the limit. If I am lucky and this limit becomes 0, I have proved my integrability. And this is possible. Why? Because the numerator is a constant and the denominator goes to infinity. So therefore, limit of b minus a f of b. So let us write and limit of this divided by n when n goes to infinity is 0. So this means that f is Riemann integral. You can prove similar thing for a decreasing function. So remember, continuity guarantees integrability. If you have continuity but you have only finitely many discontinuities, you still can guarantee integrability. Being a monoton function, monoton means either increasing or decreasing. It is also granted, it will also guarantee the integrability. Any questions? Okay. So this theorem, actually, I don't want you to prove this because this proof is a little bit technical, but I want you to understand it for one reason. Okay, so it means that if f is bounded Riemann integrable on this closed interval a and b, so let me explain it here on the board for you. So I just want you to know the content. The reason I want you to know, this is more or less, you can consider it optional, but the reason that I wanted to mention it here is because I want to use this for another theorem. Okay, so so if f is bounded and Riemann integrable, so f belongs to R, A and B. Okay, and then suppose that when you calculate, if one thing is very clear, f is bounded. So what does it mean? It means that if you calculate f on the whole domain, it becomes a bounded set. When it is a bounded set, it means that it is definitely included in an interval. Yes? If you have a bounded function, it means that the range is bounded as a set. It means that if you calculate f on all the elements and you find all the elements, it becomes a bounded set. If it is bounded, it means that it is included in a closed interval C and D. Okay? That is not something very strange. Okay, but then if you have a function phi which is defined on that interval and is continuous, yes? So you have your original function. You don't know about continuity of your original function. You only know it is integrable and bounded. So it means that its range is also included in a closed interval, whatever it is. And now assume that you have a function which is defined on that interval, but it is continuous. So in other words, you know that phi belongs to C and C and D. Then the theorem claims, it's a little bit technical to prove it, the theorem claims that f of phi is Riemann integrable. On A. Okay, so I want to take this for, sorry, the other way around. That was wrong. Phi should come first and f second, because f takes from A to B and then goes to something to C and D according to this relation, and then phi can act on this one. The other way around was not even defined in general. This is the correct. So this is the content of the theorem. So if you have integrable function and a continuous function, so continuous function composed with an integrable function remains integrable. Okay? So why this is useful? Because I don't want you to see the proof because the proof is technical, but I want you to know the theorem to prove this one. So for example, can you say why this is true? This is a very important theorem. It tells you that if, let me write it here on the board, 1210. If f is Riemann integrable on A and B, we want to prove that absolute value of f is also Riemann integrable on A and B. Yes? And you see why this is a consequence of the previous theorem. That is enough. If you can understand that this is a consequence, an immediate consequence of this theorem, then that's good. That's enough. And you see that? So here, f is Riemann integrable and bounded, of course. So I hope that you agree f is bounded. How should I know it is bounded? When I say f belongs to the Riemann, when I say f is Riemann integrable, it means that we are assuming that f is bounded, because all the theory of Riemann integrability is only for bounded functions. So f is bounded. What does it mean? It means that f of A and B is a subset of C and D, for example. Yes? Because the result is bounded, so it should be included in a closed interval. Now, let us take phi to be the function from C and D to R, but can you tell me what function I am looking for? This theorem works for every function that is continuous, but for proving this, I have to choose phi a particular continuous function. What continuous function do you think I will choose to prove this theorem? No clue. It's absolute value of x, yes? So first of all, do you agree that this function is continuous? That's the absolute value of x continuous. And now do you see that phi, if I ask you what is phi OF, what do you say? Phi OF acting on x is equal to what? Is equal to phi acting on f of x. But phi is the absolute value of any input. My input is this one, so it becomes absolute value of f of x. So this means that if I ask you what is phi OF, what is phi OF? Phi OF is the absolute value of f. Yes, because this can be written as absolute value of f acting on x. So phi OF is absolute value of f acting on x, so it means phi OF is absolute value of f. So this theorem tells me that phi OF is Riemann integrable. In this case, phi OF is nothing except absolute value of x. So absolute value of x is also Riemann integrable. Yes? For example, can you tell me why this one is true? So you have to change your phi in a way that this one proves this one for you. So can you feel how should I define phi so that it will be suitable for proving this using this theorem? Yeah? X squared. Okay? And by the way, do you see that? So if I take phi x squared, then the composition of these two becomes exactly f squared. And by the way, there is nothing very specific about 2. Do you agree that f to any power, any natural power will be also the case? But I have to change, if it is the third power, I have to define phi x to be x cubed, and etc. The reason phi squared is important is because if you read the notes, this is needed for proof of one other theorem, okay? Any questions here? So at this level is enough to know about this composition, okay? Theorem. Okay, so these are the theorems that you were already familiar with. So what is the meaning of the first theorem? It tells you that if I have two functions that are Riemann integrable, the sum is Riemann integrable, and if you multiply one of them by a constant lambda, it remains integrable. And the last one, you didn't have it in calculus, and that's the product of Riemann integrable functions is also Riemann integrable. Okay, I don't want to prove it because we don't have time, but I want you to tell you at least the last one, okay? So let me write it here for you. What we know is that I give you two functions, f belongs to the Riemann integrable functions, and g also belongs to the Riemann integrable functions. So this is 12, 11. We want to prove that f plus g is the same. We want to prove that lambda f is the same. If I ask you what lambda is a number, is a real number. One thing that I want to concentrate today, that I just wanted to learn, is that you didn't have it in the normal calculus course. The product is Riemann integrable. If I give you two functions that are Riemann integrable, the product is also Riemann integrable. Okay? But because there is no time, you have already seen these in calculus. So you see the formulas are familiar to you, yes? The integral of f plus g is the integral of f plus integral of g, and integral of lambda f is lambda integral of f. Okay, so somehow I consider, of course, the proof in analysis is much harder. It's not that trivial. I have written them in the notes for you so you can read and study, but let us concentrate here. Okay, by the way, what about f minus? I haven't written f minus, but do you think f minus g is also Riemann integrable under these two conditions? Why? It is a combination of this one and that one. Yes? Because if I choose lambda to be minus 1, it gives you the negative value, is the negative of f is also Riemann integrable if the function is Riemann integrable, and then the sum becomes the difference. So that's why I haven't written the difference explicitly, but you already know that the difference is also true. But why the last one is true? And for the last one, you see we don't have any formula. So I have written a formula for you that integral of f plus g is equal to integral of f plus integral of g. Okay? But I haven't written any formula for fg. We do not have any formula for fg. The one close to this one is integration by parts. Okay? But that's not a very simple formula. I haven't written it down there. But this one is true. Why? The trick is this. The trick is to write fg to be 1 over 4 f plus g squared minus 1 over 4 f minus g squared. Okay? So is that understandable first? Yes. Because if I raise it to power 2, f squared and this f squared, well, that's a very simple algebra, yes? The right-hand side becomes f squared plus 2 times f times g plus g squared, and then I have 1 over 4 minus 1 over 4 f squared minus 2fg plus g squared. Yes? So 1 over 4 squared, f squared minus 1 over 4 squared are gone. The same for g squareds are gone. And this becomes fg over 2 plus fg over 2 becomes fg. So this, what I have written, is true. But why this is useful for me? Remember, I want to prove that this is the case. So fg is equal to this one. F and g are Riemann integrable. So we learned that the sum is Riemann integrable. We also learned that the difference is Riemann integrable. And by this theorem, we learned that the squares are Riemann integrable. And we learned that if I multiply them by constants, it remains integrable. So you see, this one was not the one that we learned in the calculus, but this is also true. But that is a different story. What will be the value of the integral of the product, how it is related to the integral of these ones individually? We don't have any simple answer to that. Any questions here? Is that understandable? So I wrote fg in this form, and I use this part of this theorem and this part of the previous theorem to conclude that fg is also Riemann integral. Okay, so now this one is an important theorem. It tells you that if f is Riemann integrable but non-negative, okay, their integral is also non-negative. It's a very important theorem here, actually. So this is 12. So we know that f is Riemann integrable, and we know that for all x in A and B, f of x is non-negative. We want to prove that this integral, which is granted to exist because it is Riemann integrable, cannot be a negative number. Okay? This is very simple. For example, this could be an exam question because that's not a very hard one. Can you see why this is true? If I have a non-negative function, its integral, if it exists, then it is non-negative. Why is that? Let me start for a partition. So I would say let P x naught up to xn be a partition. Of A and B. Let me calculate, for example, L. this becomes sigma mk delta xk. K, I'm not talking about regular partitions, any partition. Can you tell me why this lower sum is non-negative?
You know for sure MK
Is non-negative, yes? Because this one is positive. That is the length of the subinterval. Mk is the infimum of my function on the kth interval, yes? So m sub k is the infimum of the values of my function when x belongs to the kth interval. But do you agree that all the values of the function are non-negative? So it means that this one should also be non-negative. Yes? So all of these numbers are non-negative. All these numbers are positive. When I multiply them, it becomes non-negative. And I am adding all of them. All of them are term by term non-negative. So I hope that you agree this is greater than or equal to 0. This is L. But because f is integrable, this means that the integral of a of my function is equal to the upper integral. Yes? If it is integrable, all these three values are equal. But this one is what? Is the supremum, is the infimum of the LF. Yes?
UF.
What?
Infimum of the upper sum.
Infimum.
Yes.
Yes. But so let me write it the other way around because I calculated L. So I want to have this one, which becomes supremum. Is that right now?
Yes.
Yes. Okay, but all these numbers are non-negative. Yes? So all these numbers inside are non-negative numbers, and I am looking for the supremum of them. So the supremum of a bunch of non-negative numbers is definitely non-negative. So this means that my integral, because of this condition, my integral and the lower integral are the same because I know that my function is integrable. And this one is non-negative. So it means that my integral is also non-negative. So this is a very simple theorem, actually. Any questions? Okay, so these results are very simple. Let me just immediately talk about that. This is a very, very important theorem. So you remember it, so might be you need to use it. So why this is true? As a consequence of this theorem, if a function f is less than or equal to g, and both of them are Riemann integrable, the integral of the left one is less than or equal to the integral of the right one. Yes? Is that trivial for you now? So let us do it quickly because we don't have time. Okay, so you see, the first one tells you that if f is greater than or equal to 0 and f is integrable, then the integral is positive. Now what do I have? This is what I want. F and g are both Riemann integrable. And I know for every x in a and b, I have written f of x is less than or equal to g of x. I want to conclude that the integral from a to b of f is less than or equal to the integral from a to b of g. Why is that true? So that's very simple to see. I would say let h be the difference between these functions. Okay? So do you agree that, therefore, for every x in a and b, do you agree that h is positive, h of x is positive, non-negative, I mean? Because according to this rule, the values of G are greater than the values of F. So when I subtract F from G, because G is bigger, H remains positive. Okay? But now, according to that theorem, if I know G and F are Riemann integrable, that theorem up there tells me the difference is Riemann integrable. So I know that H is Riemann integrable as well. And now this theorem guarantees that the integral of H is non-negative. But what was H? H was G minus F. But then this means that the integral of A to B G minus integral from A to B F is greater than or equal to 0. So this means that the integral from A to B F is less than or equal to the integral from A to B G. So it means that if a function is always less than or equal to another function and both of them are integrable, the integral of the first one is at most equal to the integral of the second. And this one is also a very, very important theorem. I want you to memorize it. It's a very important one. So, but why it is true? So, if F is integrable, in the previous theorem, we already saw that absolute value of F is also Riemann integrable. Okay? And now this theorem tells you how the value of this integral and the value of this integral are related. The theorem tells you they are not usually equal, but the absolute value of this integral is at most equal to the integral of this function. So this is a triangle inequality for integrals. So if you flip the absolute value inside, you cannot usually keep equality, but the right-hand side becomes greater than the left-hand side. But the proof is also extremely simple. Why? Because every function is less than or equal to the absolute value, greater than or equal to the minus absolute value. And then we are done. Yes? Because this theorem tells me that this function is smaller than this function, so this means the integral of that function is less than or equal to the integral of that function. And this function is less than that one, so its integral is less than that function. Yes? But then this minus sign can come out because of the theorems up there. So if you don't mind, let me take this minus sign out now. So I have a number, let us call it M, and let me call this number A. And this is minus A. So I have a number M which is sandwiched between two numbers, a number and its opposite. So what does it mean? This means that the absolute value of M is less than or equal to A. So from here I can conclude the absolute value of the middle one is less than or equal to A. And that is the proof for this one. But these are very simple theorems. All of them are very useful. Let us see what we have next. Okay, so let me only write this, because this theorem you have already seen it in calculus. Okay, so I will describe it. The proof is technical. If you want, you can see it in the notes. But you have seen it already in the calculus. I just explain it and we are done for today. So, if integral, first of all, let me describe this one for you because you have already seen that. Do you remember in calculus what was integral from A to A? This is defined to be 0. You can understand it. It is the area below the curve from A to A, so there is nothing. And then one thing was happening, if I have integral from 3 to 1, you remember some convention for this as well? Because usually when we write the integral, the lower number is smaller than the upper number. But in the calculus, you also had this from 3 to 1. Well, how was it defined?
can put a minus before.
Yes, put a minus sign and do it the other way around. So that's exactly the same here as well. So that is just the definition. So the definition of this is 0 and the definition of this is just the other way around. And then you have a theorem now, integral from a to b, you can, of a function, you can break it into two integrals or more integrals. You can go from a to b directly, or if you want, you can go from a to c, but provided that you add from c to b. Okay, so this theorem, you also had it in calculus, but now in the main theorem, I had mentioned that this number is between a and b. Okay, so in the proof, I am assuming that c is between a and b, but after having these two conditions, these conventions in place, you don't need to have c exactly in between a and b. For example, you can, if you know integrability, you can go from 1 to 3 by doing it like this. You can go from 1 to 7, and then you can go from 7 to 5, and then you can go from 5 to 3. This is possible. Okay? So I, of course, for this one, that 7 is greater than 5, I am using this definition. But this is completely possible. 1 to 7, 7 to 5, 5 to 3, it is the same function from 1 to 3. But of course, for this one to work, the function should be integrable on the largest interval. So if f is integrable from 1 to 7, then this is valid. Okay? Okay, but the other one, I need to probably, tomorrow I will continue these notes and then we finish the derivative. Any questions? Thank you very much.